When you think about the cosmos, there are certain universally accepted truths that we just don't question. And I feel like the very top of that list is the reputation of the supermassive black hole.
Oh, absolutely.
I mean, if you're tuning in today, you're probably picture it the same way everyone else does, right?
Yeah.
Like the ultimate cosmic monster, the great destroyer lurking at the center of a galaxy.
Just this inescapable abyss.
Exactly. An abyss that shreds stars, swallows light, and just obliterates foolish enough to get too close. It's basically the end of the line. But what if we had it completely backwards,
Yeah, that's the big question.
right? What if the universe's most terrifying executioner is actually, well, its most prolific creator?
It forces a complete paradigm shift, honestly. I mean, we're taking the ultimate symbol of cosmic destruction and rebranding it as the ultimate planetary cradle.
And that shift in perspective is exactly what we're getting into today in this deep dive.
Yeah.
Because we have a stack of incredibly dense paradigm-shifting sources in front of us.
We really do.
Yeah, so we're looking at a May 2026 science report from phys.org, written by Paul Arnold. And we are pairing that with the actual raw data, a deeply technical RSIF preprint paper led by Bhupendra Mishra, alongside Barry McKernan and their team out of CUNY.
Right, and the data there is just mind-blowing.
It is. So our mission today is to explore their radical new model that suggests active supermassive black holes. Active galactic nuclei might just be the biggest planet nurseries in the entire universe. So, okay, let's unpack this, because I need to understand how we go from destroyer of worlds to creator of millions.
Well, to map that out, we have to look at the anatomy of these supermassive black holes when they are actively feeding. We call them active galactic nuclei, or AGNs.
Right.
And the traditional view is that an AGN is surrounded by a massive swirling disk of gas and dust spiraling inward. So we naturally picture this chaotic, violent environment where matter is just being superheated and, ripped apart by gravitational shearing.
Right, like the cosmic monster having its lunch. But I gotta say, if you're listening to this and thinking, dust, really, dust is going to survive next to a supermassive black hole. I mean, I am right there with you.
That sounds impossible.
It sounds totally impossible. It's like putting a delicate snowflake in a blender. How does it not just get incinerated instantly?
So the CUNY team actually looked away from the gaping mouth of the black hole and zoomed out to the outer edges of that swirling accretion disk.
Okay.
This outer region is a really thick, dusty, donut-shaped ring called a torus. And what the math reveals is that the temperatures and the physical conditions inside these AGN tories are surprisingly similar to circumstellar disks.
Circumstellar disks. So those are the disks of gas and dust that spin around young newborn stars.
Yeah.
Where normal planets form.
Exactly. The fundamental building blocks are identical. You've got gas, dust, and rotational motion.
Okay, I understand the idea of a torus, the outer edge of the donut. But we are still talking about the immediate neighborhood of a supermassive black hole.
Yeah.
I mean, the gravity pulling inward is immense, and the radiation pushing outward is intense.
It's extreme.
Yeah, it's a tug of war on a galactic scale.
Yeah.
So how does delicate microscopic dust not just get completely shredded or, eventually lose its momentum and spiral into the center?
Well, the preprint tackles that exact mechanical problem. When they fed all the variables, like the temperatures, the gas densities, and this outer ring into a computer model, they included a crucial structural element that defines this environment: strong magnetization.
Magnetization.
Yeah. The plasma and gas in these AGN disks generate incredibly powerful interwoven magnetic fields.
Instead of just a loose cloud of dust and gas, we are dealing with something that has an internal structure. Like, I don't know, invisible rebar in concrete.
That is actually a highly functional way to visualize it. Yeah. The magnetic field lines act very much like physical rebar or tension cables running through the plasma. They resist the immense gravitational shearing force of the black hole.
Oh, wow.
Right? Because without that magnetic support, the outer disk would just succumb to the chaotic gravity, fragment entirely, or lose its angular momentum and send all its material spiraling inward.
That makes sense.
But because the disk is heavily magnetized, it holds its structure. The magnetic tension forces the gas to move in a more rigid, uniform way, creating a surprisingly calm, gravitationally stable pocket in the midst of all that extreme physics.
Okay, so the magnetic fields are acting sort of like a stabilizing track for a bullet train. Even though everything is moving at an incomprehensible speed, the track forces it to stay smooth and prevents it from flying apart. So the dust is allowed to just exist.
And not just exist, but interact. The magnetic scaffolding stabilizes the environment enough that the dust isn't constantly being ripped apart by tidal forces.
Okay, The structure holds. The dust survives the gravity. But now we have a causality problem, because dust, just sitting on a magnetic track, doesn't make a planet.
No, it doesn't.
Right. So how do we get from microscopic grains of cosmic sand to a solid, massive celestial body?
So the physics of the preprint gets incredibly specific here, focusing on a mechanism called streaming instability.
Streaming instability, got it.
Yeah. In this stabilized disk, gas is supported by its own pressure, which makes it orbit the black hole a little slower than you'd expect from gravity alone. But solid dust grains don't feel that gas pressure. They want to orbit faster.
Which means the dust is constantly slamming into the slower-moving gas, like trying to run through waist-deep water.
Yes, perfect analogy. The dust feels a continuous headwind from the gas, and this headwind saps the dust grains' momentum, causing them to drift inward. But as they drift, they bump into each other.
Oh, I see where this is going.
Right? The authors note that the dust grain sizes required to trigger this instability are easily attained through simple coagulation. They bump, they stick, they grow. And as they grow, they become less affected by the headwind, altering the way they interact with the surrounding gas flow.
So it's almost like a highway traffic jam.
Yeah.
The smaller cars are getting slowed down by the wind resistance, they bunch up together, and suddenly you have this massive pileup of material that completely changes the flow of the entire highway.
A traffic jam is the perfect framework, honestly. But the scale of these pileups in an AGN torus is catastrophic in the most creative way possible.
Thought so.
Because the torus is so thick and packed with material, these traffic jams become incredibly dense. Their collective gravity takes over. The preprint calculates that this streaming instability produces massive dust filaments that contain entire solar masses of material.
Wait, a solar mass? As in the mass of our entire sun, but made entirely of clumped-up dust?
Entirely solid material, yes. And under their own immense weight, these solar mass dust filaments collapse and fragment. We aren't talking about forming one or two little rocks here. A single filament collapses into tens of millions of planetesimals.
Tens of millions of seeds for planets.
Yep.
From one single filament. That's hard to wrap my head around.
The model predicts an absolute explosion of planetary assembly. These planetesimals range from the mass of our Earth all the way up to super Jupiter masses.
Okay, but if you have tens of millions of planetesimals forming simultaneously in this donut of gas, they must be aggressively competing for resources. How fast are these things actually growing in this environment?
Staggeringly fast. Because the environment is so dense with material compared to a normal star system, the growth rate breaks all conventional timelines. The researchers explain that these planets are generally born in what's called the 3D Bondi regime of pebble accretion.
3D Bondi regime. Okay. If a normal planet forms in a flat 2D circumstellar disk, does 3D mean this thing is pulling in dust from above and below it simultaneously?
You are tracking the mechanics perfectly. Yes. In planetary physics, there are different ways a young planet sweeps up material. The preprint notes that geometric accretion and 3D hill accretion happen here too.
Okay.
Geometric is basically a planet sweeping up only what is directly in its orbital path, like a snowplow. And hill accretion is when a planet's gravitational reach captures material, but it's constantly battling the host star's gravity, which limits its sphere of influence.
So the planet has a limited reach before the star just steals the dust back.
Right, but the 3D Bondi regime is dominant in the AGN torus. Bondi accretion relies heavily on the ambient density of the gas and the relative velocity of the material flowing past the planet.
Which is very high in this case.
Exactly. Because the torus is so incredibly thick, dense, and fully enveloping, the young planet is suspended in a highly pressurized fog of raw building materials. Its gravity pulls from all three dimensions spherically.
It's not just a vacuum cleaner on a flat floor. It's a spherical vacuum cleaner suspended in the middle of a dust storm, pulling from every single direction at once.
Yes. And because of that constant spherical inflow, the mass doubling time, which is the time it takes for the planet to become twice as massive, is estimated to be anywhere from 1,000 years to 10 million years.
Wait, 1,000 years?
Yeah.
In cosmic terms, 1,000 years is literally the blink of an eye. If it's sitting in a fire hose of dust and jubbling its mass every 1,000 years, the gravity and internal pressure of that, cosmic dust bunny must be skyrocketing.
Right.
Does it just grow until it swallows the whole torus? What stops it?
That is the pivotal question the CUNY team addressed, and it challenges the fundamental boundaries of planetary physics.
Okay.
In a normal stellar disk, a planet like Jupiter grows until its gravity consumes or scatters all the material in its immediate orbit. It basically carves out an empty ring in the disk. We call this gap carving.
Right, right.
Once the gap is carved, the food supply is cut off and the planet stops growing. That limit is closely tied to a concept called the pebble isolation mass.
So the gap acts as a natural cutoff valve. No more dust nearby, no more growth.
Exactly, but in the Aegean Taurus, the environment is so deeply magnetized, the gas is so pressurized, and the turbulence is so high that gap carving fails completely.
It fails.
Yeah, if a planet tries to carve a gap, the magnetic turbulence and the sheer volume of inflow instantly refill it. The cutoff valve never engages.
Oh, wow.
The preprint calculates that the pebble isolation mass in this black hole environment is actually pushed completely beyond the hydrogen burning limit.
The hydrogen burning limit.
Yeah.
Wait, if I'm remembering my astrophysics correctly, that's the mass threshold where an object has so much internal pressure and heat that it ignites nuclear fusion. Are you saying a planet grows so fast and so large that it turns into a star?
The math dictates that because they don't carve a gap, these objects can just keep accreting gas and dust concurrently, blowing right past normal planetary limits. The researchers note that a planet can attain crossover mass while still in the planetary mass range, leading to vigorous runaway gas accretion.
Which means
They pull in so much gas that their cores reach the pressure needed for fusion. The authors explicitly state this defines a core accretion channel for star formation.
that is mind-bending. A planet is born from dust, eats an ocean of gas because the buffet never closes, catches fire, and turns into a star, all while orbiting a supermassive black hole.
And because of that, their growth isn't stopped by gap carving. It is only stopped by stellar feedback. The object actually has to ignite, and the explosive thermal energy and solar winds from that nuclear ignition are what finally create enough outward pressure to blow their remaining gas away and halt the accretion process.
Oh, wait. Here's where it gets really interesting for me. I'm looking at the notes from the preprint here, and it predicts a population of exotic objects.
Yes.
If this pebble isolation mass is pushed beyond the stellar ignition point, what happens to the objects that sweep up dust but miss out on the gas? The paper says the tortoise can form objects directly above the hydrogen burning limit that are made of pure dust, unlike anything known in ordinary planetary systems.
This is perhaps the most radical proposition in the entire model. I mean, we classify celestial bodies based on how they form and what they are made of. A planet forms from core accretion of heavy elements, right?
Right.
And a star forms from the gravitational collapse of a hydrogen and helium gas core. But here we have the mechanism of a planet dust coagulation and pebble accretion, resulting in an object with the sheer mass of a star, but lacking the hydrogen envelope necessary to ignite fusion.
Right, because if it doesn't have hydrogen, it can't catch fire.
Yeah.
So you have something heavier than a star with the crushing gravity of a star, but it's just a solid sphere of rock and dust.
Yeah.
How does something like that even exist without collapsing into a black hole itself?
Well, it wouldn't collapse into a black hole unless it crossed the Tolman-Oppenheimer-Volkoff limit, which requires much, much more mass. Instead, it would just compress into a heavy, dark behemoth.
A dark behemoth.
Yeah. The internal friction and immense gravitational pressure would generate tremendous heat. It might glow a dull, menacing infrared, but it wouldn't shine with the nuclear fire of a true star. It bridges the gap between planetary science and stellar astrophysics in a way we've never really had to grapple with before.
A dark, pure dust behemoth radiating sheer heat. Do we even call that a planet anymore? Or is this a completely new category of celestial body?
It's hard to say.
Right. But whatever taxonomic box we put it in, the sheer volume of these objects is what's getting to me. The phys.org article quotes the researchers directly, saying, "Our approximate model suggests that AGN Dustary hosts the largest populations of planets in the universe." We aren't talking about a few weird anomalies hiding out in space here.
No, the implications are staggering. The single largest population of planets in the universe might be hiding right outside the event horizons of supermassive black holes.
If you connect this to the way we've historically searched for life or even just exoplanets, it feels like we've been looking in the quiet suburbs while completely ignoring the biggest metropolis in the galaxy.
If we connect this to the bigger picture, it forces a complete reevaluation of the galactic life cycle. We have spent decades fine-tuning our telescopes to look for tiny dips in starlight, to find exoplanets in quiet suburban neighborhoods of the Milky Way.
Yep.
And all the while, the most crowded, bustling planetary environments might be located in the most hostile regions imaginable. It blurs the line between planet and star. It shows us that the universe's mechanics for creation are far more robust and honestly far less restrictive than our classical models assumed.
It really is a complete perspective shift. But I do want to bring us back to Earth for just a second. I know if you're listening right now, your imagination is probably running wild. But both the phys.org article and the preprint authors are very careful to point out that these are currently approximate computer models and highly complex mathematical calculations.
Very.
Right? They fed the physics in, and the math dictates that this should be happening. But as Paul Arnold writes in his article, astronomers now have plenty of food for thought, but they need actual observational evidence to support these ideas. We haven't actually pointed a telescope and seen one of these pure dust giants yet.
That is a crucial distinction. Theoretical physics points the way, but observational astronomy has to verify the destination. The challenge, of course, is that peering into the torus of an active galactic nucleus is incredibly difficult.
I can imagine.
Yeah, the glare of the accretion disk, the sheer distance, the thick veil of dust finding a planet, even a massive one, in that blinding light is a monumental technological challenge. But this paper gives astronomers the exact mathematical signatures to start looking for. It gives them the thermal emissions and the kinetic disruptions to scan for.
And until our telescopes catch up to the math, we are left with this incredible new theoretical reality to chew on. Think back to what we said at the very beginning. We've always looked at supermassive black holes as these terrifying, solitary monsters in the dark, the ultimate dead end of the universe.
Right.
But based on this deep dive, I want you to leave with a completely different image in your head. Imagine standing on the surface of one of those exotic, pure dust worlds. A planet heavier than a star, forged in a cosmic traffic jam, stabilized by invisible magnetic scaffolding.
It's an amazing thought.
If you looked up into the sky, you wouldn't see a quiet smattering of distant stars. You'd be looking up at the blinding, roaring engine of an active galactic nucleus taking up half the sky. And sharing that single cosmic neighborhood with you, crammed into that same torus of dust, would be tens of millions of massive sibling planets. A sprawling, chaotic nursery of worlds, born in the very jaws of the universe's ultimate destroyer. Keep your eyes on the stars, or in this case, the black holes.